we are going to pause for a second. We're going to pause talking about energy and work just for a second because I want to introduce these new things called springs. You may have heard of them. But I want to talk a little bit about springs before we go on to talk about work again. So we're just introducing springs just for a second, then we'll go back to talking about work and energy. So what I have here is a spring. It's attached to a wall. We are going to assume that all of our springs have no mass. That just makes everything much simpler. I also have this block attached to the spring because since this does not have a mass, I'm always going to be looking at what force does the spring exert on something else. So this is kind of the mass, like some block here. The spring is going to exert a force on this mass. So one thing we can think about a spring is that it exerts what is called a restoring force. And a restoring force, it just means that the direction of the force is always trying to get the spring back into a certain position. Okay, so the spring exerts a force. This is a new type of force. We can add it to our list of all the types of forces that we know. You know, we know about tension, the normal force, the force of gravity, friction, and now we can also say the spring force is another one of the forces that we know about. So let's look at what it means to be a restoring force. That's the type of force that the spring force is. First, we can recognize that springs have a natural length. Okay, it's the length of the spring when it's not being stretched or compressed. And so what I can do is I can, kind of say this position right here is the equilibrium position of this spring and this mass here. It's in equilibrium because there's no forces on the mass. The spring is not being stretched or compressed. The spring is in its natural length. So I'm just going to mark this position as the equilibrium position. Here, so the equilibrium position is kind of measured where the end of that spring is. Here, the spring has been compressed to the left, okay? Because now the edge of the spring is right over here. It's been pushed over to the left, so the spring has been compressed. And I can say it's been compressed by a distance delta x, and it's being compressed to the left. So the spring, in this case, will exert a force on the mass, and the force the spring is going to exert is going to try to restore the spring back to its equilibrium position. So that means the force of the spring is going to be to the right. So this is why we call it a restoring force. It's always pointing back towards that equilibrium position. Similarly, if we stretch the spring out, so now the spring has been stretched to the right, so there's this displacement to the right, there's a delta x to the right. At this point, the spring is going to be pulling the block back to the left. That's going to be the direction of the spring force. Okay. And we can calculate how big the spring force is. This is the formula that lets us calculate how big the spring force is. So this is the force exerted by the spring. This is just a normal force. It's going to be measured in newtons. Sorry, it's a usual force, not a normal force. A regular force measured in newtons. It's going to be equal to negative, we'll talk about the negative in a second, k times delta x. So K is a property of the spring. It's called the spring constant. It just tells you how strong the spring is. Okay? Very strong springs, like the things you might find in the shocks in your car, K for those springs will, might be like 10,000. That's how big the number is because it's very, very strong. K for a really weak spring, like a slinky, will be really, really small value. The units for K, the spring constant, are newtons per meter. So that kind of tells you what it's measuring. It's measuring how many newtons of force do you get per meter that you stretch the spring. So something like the shocks in your car have a huge spring constant because if you compress them just even a teeny tiny bit, they give you a big force out. Something like a slinky has a much smaller spring constant because you can stretch it out a huge amount and you just get a small force. Delta x measures the distance the spring was stretched or compressed with respect to that equilibrium position. So let's talk about what the negative means. The negative is just indicating that the direction of the force is opposite the direction of delta x. That's all that it's showing you. So when delta x was in the negative direction, the force is in the positive direction. When delta x was in the positive direction, the force is in the negative direction. That's the only thing that this negative means. When we draw free body diagrams, I show the direction just based on how I draw my arrow for the force. So what I want, what that number that I'm going to use in my net force equation, I ignore the negative sign because I have already figured out what the direction is when I draw my free body diagram. But you'll see that in the next example. A very useful thing is to set your equilibrium position at x equals 0. You get to choose where your x equals 0 is, so you might as well put it at the equilibrium position. Because when you do that, delta x is measuring how far you are from your equilibrium position. So it would be like, delta x would be like, what is your x position now minus your x position of your equilibrium. But if your x position of your equilibrium is 0, then you can just say that this spring force is equal to negative k times x, where x is the position of the end of your spring at that moment. Okay, so for example, if this is my x equals 0, and you can imagine this is like a number line here, I can just measure what is this x position, and that value is what would be my delta x here. So I can just put that x position into this equation. Okay. Let's work through an example. And again, we're kind of ignoring energy and work just for a second so we can practice a little bit with springs. So press pause, try to work through this one, and then we'll go through it together. So I have something hanging from a spring, and I want to know how far is the spring stretched. Okay, so I'm going to look at the object that's just hanging there, and I'm going to look at the forces acting on it. I have gravity pulling down, and I have the force of the spring pulling up on it. And so I'm going to look at my net force in the y direction. In the positive y direction, I have the force of the spring. In the negative y direction, I have mg. My net force in the y direction is always, always, always equal to my mass times my acceleration in the y direction. And this object is hanging at rest, so my acceleration in the y direction is 0. I've also substituted in that the force of the spring is equal to k times delta x is what we saw before, but now that spring is going vertically, so I'm going to call it a delta y. You also might be worried, why didn't I put the negative in there? Well, the negative just tells you what the direction is, okay? The negative just tells you the direction, and I've already taken care of the direction by saying that the spring is pulling up on our object. So I don't want to make this negative because that would be like saying the spring was pushing downwards on the object, which it's not doing. So I've already in my mind taken care of the fact that delta y was downwards, so the spring force was upwards. So I don't need the negative there. Okay. Here I plug in all the values that I know, and then I can solve for my delta y.